Good morning, curious minds. Look around you. From the ancient pyramids to the latest smartphone, everything we build eventually degrades, eventually ages. But what about us? What about the human body, this incredibly complex living machine? For millennia, aging has been accepted as an inevitable, perhaps even philosophical part of life. But what if aging isn't just a passive decay, but a highly intricate, even programmable process? And what if, just like we create digital models of buildings or cars to predict their performance, we could create a virtual version of ourselves, powered by artificial intelligence, to unlock the secrets of our own longevity? Today we embark on a fascinating journey into the modern science of aging, a field bursting with breakthroughs. And at the forefront of this revolution is a concept that sounds like science fiction, but is rapidly becoming reality: the digital twin, supercharged by the analytical power of artificial intelligence. To understand where we're going, we first need to understand the fundamental why. Why do our bodies, seemingly so robust, begin to show signs of wear and tear? Our first clue lies at the very heart of our cells, within our DNA. Imagine the ends of your shoelaces. They have those little plastic tips, right? These tips, called a glaze, protect the laces from fraying. Now, think of your DNA strands, coiled tightly within every cell, as incredibly long shoelaces. The protective tips on our DNA are called telomeres. Every time one of your cells divides to repair tissue, grow hair, replace skin, these telomeres get a little bit shorter. It's like a molecular clock ticking down with each division. This natural process, known as telomere attrition, is one of the earliest signs of aging. Once those shoelace tips are gone, the cell can no longer divide safely. This is a crucial programmed limit, first observed by Dr. Leonard Hayflick decades ago, known as the Hayflick limit. But here's where the idea of a digital twin, powered by AI, becomes truly revolutionary. Imagine having a precise, virtual replica of your body, a digital you. This digital twin, fed by a torrent of data from your wearables, your genetic profile, your lifestyle choices. And advanced medical imaging could model the length of its virtual telomeres in real time. But it's not just passively displaying data. AI algorithms are constantly analyzing this information, learning your unique biological rhythms and patterns. It could show you not just an average, but your unique cellular countdown, providing predictive insights into your biological age, far beyond your chronological one. AI allows it to sift through millions of data points to identify subtle changes, often long before they manifest physically. It's like having a personalized early warning system for your cellular health, constantly learning and refining its predictions about your future. So what happens when a cell reaches its Hayflick limit and can't divide anymore? Does it simply die? Not always. And this leads us to our second clue in the aging mystery, the zombie cell problem. Instead of dying, many of these cells enter a state called cellular senescence. We call them zombie cells because they don't function properly, but they also refuse to die, and worse, they start releasing a toxic inflammatory goo. Scientists call it the senescence-associated secretory phenotype, or SAS. This SASP is like a corrosive agent, damaging healthy neighboring cells and creating a cascade of inflammation throughout the body. It's a major driver of many age-related diseases, from arthritis to heart disease. Think of it, just a few rogue zombie cells can wreak havoc on an entire neighborhood of healthy cells. Your digital twin, utilizing advanced AI models, could become an incredible diagnostic and predictive tool here. Imagine it simulating the accumulation of these zombie cells in different organs and predicting their impact on your joint health, your cardiovascular system, or even your cognitive function. AI can identify patterns in inflammation and cellular stress, allowing for highly personalized insights into areas of vulnerability and even modeling the potential effectiveness of future senolytic interventions. Therapies designed to remove these zombie cells. This isn't about scaring you. It's about empowering you with foresight, powered by intelligent data analysis. For a long time, scientists thought aging was primarily about DNA damage accumulating. But our third and perhaps most mind-bending clue points to something even more subtle: the information theory of aging. Think of your DNA as the digital information on a CD, the hardware, the music, the entire blueprint of you is encoded there. Now, the epigenome is like the surface of that CD, the software. It tells your cells which genes to read and when. It's the operating system for your biology. With aging, the hardware largely remains intact. But the software starts accumulating scratches. These scratches don't change the underlying DNA sequence, but they make it harder for your cells to read the instructions correctly. The song is still there, but the player can't read it perfectly. This loss of epigenetic information is now considered a primary driver of aging by leading researchers like Dr. David Sinclair at Harvard. The sheer complexity of these epigenetic patterns is where AI truly shines, as it can identify subtle shifts and predict consequences that human analysis alone might miss. And once again, your digital twin, armed with AI, could be the ultimate tool to visualize this. Imagine seeing the scratches on your virtual epigenome, understanding how different environmental factors or lifestyle choices might contribute to this information loss. More importantly, AI could simulate how certain interventions might polish that CD, potentially restoring youthful epigenetic patterns. AI's ability to process massive datasets from epigenetic clocks and other biomarkers makes it indispensable for this level of personalized insight. This brings us to our fourth clue, a truly groundbreaking revelation: the reboot possibility. If aging is partly a loss of information, can we restore it? In truly astonishing experiments, scientists, building on the work of Dr. Shinya Yamanaka, who discovered the Nobel-winning Yamanaka factors, have shown that it's possible to polish the scratches off the cellular CD in mice. They've managed to partially reboot the malfunctioning computer of aged cells, storing youthful information and reversing signs of aging in tissues like the eye and brain. This is epigenetic reprogramming. Now, this research is still in its very early stages and has only been observed in animal models. It is not a therapy available for humans today. However, the digital twin becomes an ethically sound, accelerated testing ground for such radical approaches. Instead of potentially risky trials on humans, these reboot strategies could first be simulated and refined on your digital twin. AI plays a pivotal role here, running countless what-if scenarios, predicting outcomes, optimizing dosages, and identifying potential side effects in a virtual environment. This dramatically speeds up research, significantly reduces risk, and helps personalize future therapies down to the individual. The potential for personalized, safe, and effective future therapies guided by AI is immense. So, what can we do right now without a personal digital twin in our pocket or access to experimental therapies? This leads to our fifth and most actionable clue: biological software maintenance. The exciting news is that while science races forward, we already have powerful tools at our disposal to influence our epigenome and cellular health. These are our biological software maintenance tools. Diet. Research from institutions like Harvard and the National Institute on Aging consistently suggests that a balanced diet rich in whole foods, fruits and vegetables, and low in processed foods may support cellular health and a healthy epigenome. Think of colorful plant compounds as potent polishing agents. For your cellular CD, AI is already being used to analyze dietary patterns and their impact on health biomarkers. Exercise. Regular physical activity is associated with supporting telomere length and reducing the accumulation of those zombie cells. It's like defragmenting your biological hard drive, keeping everything running smoothly. Your digital twin could, in the future, recommend the precise type and intensity of exercise best suited for your unique biological profile, based on AI analysis of your activity data. Sleep. Quality sleep is crucial for cellular repair and maintaining epigenetic integrity. It's when your body performs its essential nightly software updates and error corrections. AI in sleep trackers is already providing valuable insights into sleep quality, and a digital twin could leverage this to optimize your restorative periods. While we await the full realization of personalized digital twins, these foundational pillars remain incredibly powerful. And in the future, your digital twin, continuously updated and analyzed by AI, could provide personalized real-time feedback on how your specific diet, exercise, and sleep habits are impacting your virtual aging markers. It could offer tailored, AI-driven recommendations that are truly unique to you. It's moving from generic advice to hyper-personalized strategies for optimal longevity. Imagine a smart coach that knows your biology intimately, learning and adapting with you. The journey to truly understand and influence aging is one of the most exciting frontiers in science. From understanding the microscopic mechanics of telomeres in zombie cells to the profound implications of epigenetic information loss, we are uncovering the very operating system of life. The concept of the digital twin, driven by the unparalleled analytical power of artificial intelligence, is poised to revolutionize this quest, allowing us to simulate, predict, and ultimately personalize our approach to health and longevity in ways we could only dream of before. It's critical to remember that while the promise of future interventions like senolytics, therapies that target and remove zombie cells, or widespread epigenetic reprogramming is immense, these are currently experimental and in early research stages. They're not available as anti-aging therapies today. Similarly, while digital twins and AI hold incredible promise for personalized health and longevity research, their full clinical implementation is still evolving. Ethical considerations, data privacy, and the need for rigorous validation are paramount as these technologies develop. Our focus should always be on evidence-based practices and consulting with healthcare professionals for personalized medical advice. The future of longevity isn't about immortality. It's about extending our healthy years, our health span, so we can live vibrant, fulfilling lives for longer. And with the help of powerful tools like the digital twin, supercharged by artificial intelligence, we are closer than ever to unlocking that incredible potential. Thank you for joining us on this journey. If you found this fascinating, please like this video, subscribe for more deep dives into science, and share your thoughts in the comments below.